How's the exam?
Better, but still bad.
Was it? We're not done. We're not finished grading. I've not looked at your exams. I've graded that. So what we do is we grade. One professor grades one question, other professor grades other question, and the third professor grades the third question. So I graded question number one, but I've not graded our section. I've graded the other sections, and the performance was not that great. People got the second question right on the relative velocity, but other four questions people struggled. But that's not about this class; it's about the other classes. So I don't know. I'll come to know today. I'll hopefully post the uh, grades on Gradescope by either tonight or tomorrow or midday. Okay, so you'll have it. We can talk about it on Wednesday. Was the time okay, or you were crushed for time?
Yeah, I feel like I ran out of time.
Too long? Okay.
I didn't realize I spent so much time on one question.
Yeah, you cannot. Yeah, you cannot afford to spend too much time on one question, otherwise you can't. Anyway, so let's talk about it on Wednesday. Okay, so okay, so this is chapter 13. Specifically, we are going to do apply Newton's laws in rectangular coordinates. So you'll see that the next three classes are going to be Newton's laws, rectangular coordinates, tangential coordinates, anti-coordinates, and the polar coordinates. Okay, so I'll review a few things before we solving problems. So for all questions in this chapter, essentially it's a three-step process. Okay, and I wrote this down earlier. First step is draw a free body diagram. The second step is apply Newton's law. Well, really third law. In this case, the problems we are going to talk about today are problems where we can express the motion of the particle in XYZ coordinate frame in the XYZ direction. So what we'll do is we'll apply Newton's law along the X direction, or md square x dt square. Fy is may equals m d square y dt square, where
Wouldn't that be the second law?
good point, second law, Fy are external forces. Examples would be spring, gravity, friction, and so on. And the last step is, and this is optional, sometimes you're asked to find the acceleration, in which case you stop at step number 2. Sometimes you're asked to find position or velocity. So if asked to find v or r, then you need to integrate the equations of motion. Okay, so if you follow these steps meticulously, one is you'll get partial points for doing free body diagrams and applying Newton's laws. The other thing is there's a higher chance that you'll get the problem right because you didn't skip any step. Okay, So one thing about drawing free body diagram is that it's really a free, the word free is very important. That is, if you're given an object, for example, let me just illustrate some points about FBD. Okay, so if you're asked to draw FBD for this system, right? A mass moved on level ground. You got to draw the FBD. So clearly there's a normal force, there's gravity. So a common way of drawing it is, well, you just take the diagram. What people do is, given that figure, they'll, on top of the figure, they'll draw forces, and this is incorrect. And the reason is because this body in this case is not free. It's still stuck to the ground. You should not show the ground when you draw the free body diagram. So what I recommend is you should never try to draw the free body diagram on the original problem, because you'll invariably get it wrong. The right way to do it is to remove the ground, that is not show the ground, show the forces, and that's the right way of drawing the free body diagram. The reason why this is wrong again is when the effect of the ground, right, is replaced by the normal mg force. So when you draw the normal force, it means that the ground has been removed from the picture, right? If you show the ground and you show the normal force, that's not right, because the ground, that force N is an internal force which is acting between the body and the ground. In fact, when you remove the ground, if you draw a free body diagram of the ground would have a force N acting downwards, which will be that when you put the two things together, the forces will cancel off. So internal forces will not come in the free body diagram. So here's another example which illustrates how people draw incorrect free body diagrams. And this is a problem you might see in the homework or in the exam. So if you're asked to draw the FBD, well, before I draw the FBD, in this case there are two masses, M1 and M2, right? And if there are two masses, then you should be able to draw three free body diagrams. The three free body diagrams are one for mass M1, M1 for mass M2, and if you wanted, and this is very depends. You don't have to really draw three free body diagrams. Depends on the problem. You can draw a free body diagram of M1 and M2 combined. So the three free body diagrams would be So that's the free body diagram of mass M1. Note that I removed the ground and I replaced the effect of the ground with the normal force. So when I show the normal force, I'm not allowed to show the ground because the effect of that is replaced with the normal force. For M2, it will be this. And if you want to draw the combined free body diagram, so this is a free body diagram of M1, M2, and the pulley is massless. Okay, is that right? so I did not show the tension. That's right, because the tension is an internal force. So if you show the tension here, that's an incorrect free body diagram. Right? What has happened is I cut the string, and that's why I showed the tension. The string here is not cut, so if the tension is not supposed to be in the free body diagram. I think I'm missing something here. This is not a complete free body diagram. So how is the pulley connected to the ground? It just can't be floating freely, right? There's something which is keeping the pulley in place. So there is a force acting on the pin joint. So I need to show that too. So let's call that Ry and Rx. So those forces are the forces which come because the pulley is connected to the ground. There are multiple ways of doing this. You could draw it, well, you could draw it in any direction. As long as you show Rx, Ry, that's fine. You could also show it at an angle. So then it's a matter of finding the force, the magnitude, and the direction of the force. Okay. Another important thing is that when the pulley is massless, the tension actually carries forward. What it means is that the tension here should be the same as tension there. If the pulley was not massless, and this is something which we'll do later on the next, I think in the next chapter, we'll do problems where the pulley is not massless. If the pulley is not massless, then the tension here is different from tension over there, which means that this will be T1, there will be T2, and then we'll have to draw a free body diagram for the mass because that mass is not equal to 0. But for now, for this problems where pulley is massless, you just draw free body diagrams for M1, M2, and the combined system. So the reason why we emphasize that you draw free body diagrams, and remember this, draw free body diagrams, A, is because you get partial credit. Second thing is that what I've realized is when people do not draw free body diagrams, they forget to include certain forces in the problems, which means that Newton's law is not right, and then they get the answers wrong. So drawing a good free body diagram is very important. Okay, so whenever you see a problem on kinetics, which is what we're going to talk today, please draw a free body diagram. So here's the first question. So if the force F is 150 newtons, determine the velocity of the 50 kg block A when it has risen by 3 meters starting from rest. Okay, first of all, what you notice is that you've seen problems like this before in the previous chapter, chapter 12, right? The only difference between those questions and this question is that at point B, you were either given the velocity of B or the acceleration of B, and you're told to find essentially the same question, but you're given force, you're given the acceleration or velocity at B. In this case, you're given a force at B, which means that in order to find the acceleration from the force, you got to use Newton's laws. So that is why this is a problem on kinetics and not kinematics, which we did in the last chapter. So we have to use Newton's laws. So once you know that we don't have to use Newton's laws, what we do is we draw free body diagrams, write Newton's laws, and then solve for velocity or position as needed. Okay, so let's draw free body diagram of, well, there are 3 pulleys, so I'll draw free body diagram, at least 3 free body diagrams. So let's start with the first pulley. So let's give it a name. Let's call it D. Okay, the only force I know is the force F acting on the left side. The string on the right, and then there is a string which connects the pulley to the wall. Now what's not given, and this is, you can assume this, is that the pulleys have zero mass or they're massless. The second assumption is that the string is inextensible, that is, it cannot stretch. So a consequence of these two assumptions is that the force actually gets transmitted. That is, the force on the left side of the pulley is the same as the force on the right side of the pulley. So this is going to be F. So this is the assumptions give you that. So as I said earlier, later we'll see problem when the pulley doesn't have mass. You have a question?
They're opposite, right?
I'm going to draw that, yeah. So I forgot to write this, but there's going to be a force upwards here. This is 2F. And the reason it's 2F because the net force in the y direction is 0, right? Okay, so then I'll draw a free body diagram for C. And it actually is much easier if you draw it right below D. So again, this is going to be F. It's going to be F this side. It's going to be 2F. That's C. And then finally, free body diagram for the last pulley. Okay, 2F. It's going to be 2F because again the pulley is massless. And what's this for? It's going to be 4F. Okay, so final free body diagram is that of a mass A. That's 4F pulling it up. And then there's mg pulling it down. Mg will be equal to 4F provided the system is in equilibrium. The system is not in equilibrium, so mg is going to be greater than 4F. So we'll see that in a bit. So second step is to write equations of motion. Okay, so things are, in this case, the system is moving along the y-axis. There's no motion in the x-axis, so it makes no sense to write the equation in the x direction. So I'm going to write Fy equals ma. Fy is may. So that is all the Fy is all the external forces, which is mg acting down minus 4F is ma, which is m d square by dt square. Okay, so I've made the assumption that this system is, well, I think this is not right. Okay, so my bad. The system moves up. So actually this is, if the system moves up, then 4F acts upwards, so it's positive, and mg moves downwards, so it's in the negative direction, right? So again, this is something which the book may not mention, but first you draw a coordinate frame, which in this case is upwards is positive, and then you write the force in that coordinate frame. So 4F is positive because my coordinate frame is positive upwards, and mg is downwards, so it's negative. Okay, so the mass is 50 kilograms, gravity is 9.81, the force F is 150, is m or 50 t square by dt square. So this gives me So what I get is d square y dt square, or this is equal to ay equals 2.19 meters per second square. And the third part is the question asks you to find the velocity when the block A has risen by 3 meters. So find the velocity when h or y is 3 meters. Okay, so we know the acceleration, we know the displacement, we need to find a velocity. So what is the expression which relates the velocity to displacement? This is going to be uniform speed, uniform acceleration motion. So you can use one of the three formulas. One of the formulas in that, this is going back to chapter 12. V square minus V0 square is 2ay times y, right? So V square is unknown, the initial velocity is 0, acceleration is 2.19, and displacement is 3 meters. So we can solve for velocity, comes out to be 3.62 meters per second. Any questions? Okay, so if you is shown on the graph. So the force that this motor exerts is shown in this graph. Determine the velocity of the 400 kg crate A when the time is 2 seconds. Okay. Again, the key thing here is to realize that you're given a force and you're told to find the velocity. So if you're given a force, you have to use kinetics. You have to use Newton's laws. So which means that you have to draw that, you have to use those 3 steps which I talked about. So let's start off with free body diagram and move from there. So let's draw a free body diagram for the, well, in this case, we just need a free body diagram for, we don't really need one for F for M, because we know there's a force F, and the same force gets transmitted. So if you draw a free body diagram for this pulley and this mass, that should suffice. So we'll draw a free body diagram for the pulley. So that's going to be F. The reason why the force on the right side is F, because the cable is inextensible, so it's a force F. But the same force should carry forward to the other end of the cable. So that's going to be F on the left side, which means that the net force downwards is going to be 2F. And then 2F mg. So FBT. Okay. In this case, there's no dynamics in the x direction, so we are only interested in motion in the y direction. So I'm going to write the equation in the y direction. Let's assume that y is positive upwards. So 2F is positive, mg is negative, is mass times ay, which is mass times d square by dt square. So we can simplify this and write, so solve for ay, that gives me 2f divided by m minus g. Okay, now here the force here is this force comes from here, right? The force is not constant. So previous problem, the force which was applied was constant. In this case, the force is not a constant.
So we could get like AY with respect to T.
Yeah, so you'll have to take that f equals 625 t square, plug it there, and then integrate that equation. However, there's a catch, which is initially the block A is resting on the ground, which means that the tension is zero, like as it's shown there, F is zero. But clearly, if you apply a force, this mass will not start moving up until the force is at least equal or greater than mg, right? So there will be a period of time where acceleration will be zero, and that will be when the force, so when the force reaches a value of, well, 2F equals mg, that's when the tension will be non-zero, and that's when the block A will start moving up. So that's the key thing which you got to know before you can't just blindly plug in the formula for F and solve this. So let me write that down. So F is 625 t square. That equals mg. So m is 400 and gravity is 9.81. So we can solve for t. T is 400 times 9.81 divided by 2 times 625. And since it's t square, so it's going to be square root. So this comes out to be 1.772. Okay, what it means is that for the first 1.772 seconds, block A is going to have zero acceleration because the tension in the cable connecting A to the pulley is not sufficient to start lifting it or moving it upwards. So it's only after 1.772 that you start moving. So the mass starts moving after 1.772 seconds. So how do we find the velocity after 1.772 seconds? Well, we use this equation now. It says AY is, what's AY? It's dVy dt equals 2 times F. F is 625 t square divided by 400 minus 9.81. So this comes out to be, so I got 1.563 t square minus 9.81. So dVy dt equals 1.563 t square minus 9.81. So dVy is 1.563 t square minus 9.81, the whole thing times dt. And so we are asked to find velocity at time t equals 2 seconds, right? So Vy is the velocity at 2 seconds. The initial velocity, so velocity at when it starts moving is, it's about to move, is 0. And the time actually goes from 1.773 to 2 seconds. So this is 1.563 t cubed divided by 3 minus 9.81 t. The upper limit and the lower limits is 2 and 1.772. Okay, so Vy equals 0.301 meters per second. So another important thing here is that note that the force or the acceleration is not a constant, it is a function of time. When acceleration is a function of time, you cannot use the formula which we used previously, which was uniform acceleration formula, right? The analogous part when the acceleration is constant is v equals v minus v by 0 equals at is the formula when acceleration is constant. In this case, acceleration is not a constant, so you're stuck using calculus. You're stuck with integration. You cannot just use the uniform acceleration formula. That was actually a very common mistake I found with when I graded the exam. There was a question where there were two gears moving, right? One of them had acceleration, which was not constant. People did use the other formula. They should use something like this to solve it. I do not know what you guys did because I graded today. Okay, so remember, uniform acceleration, you can use a simpler formula, which we derived, but non-uniform acceleration, you've got to integrate. There's no way out. Okay, so here's the problem on springs. So this is a 2-pound collar. C fits loosely on the smooth shaft. Okay, it's a smooth shaft, so there's no friction. If the spring is unstretched when S equals 0, so S is this. So clearly when the collar is vertical, as you can see, uh, the the stretch is 0, and the collar is given a velocity of 15 feet per second. Determine the velocity when find the velocity when s equals 1 meters. Okay, another important thing which actually is not given in this question is this setup is not in the vertical plane, it's in the horizontal plane. What that means is that gravity is not going to be acting that way. There's no gravity because this thing is this way. The mass is moving in this plane. The collar is moving in this plane. So gravity is going to be normal. So it's not going to be working against or in the direction of the spring. Okay, again, in this question, you are given a spring. The mass moves because there's a spring involved, and you know how to compute the forces due to a spring. So if you know the forces, you can then find the acceleration using Newton's laws, and then do kinematics or position. So this is a problem involving F equals ma, and not simply kinematics, which we did in chapter 12. So let's start following those the three things we talked about. Draw free body diagram. Now one thing to remember is when you draw free body diagram for such a system, do not draw a free body diagram in that position. Okay? Draw it at some position, like say at distance s. If you draw the free body diagram for that position, that doesn't generalize to a generic case. So you're better off drawing the free body diagram for a generic case or a generic point s in the motion. So this is S. Okay, I'm going to show the forces due to the spring. The property of a spring is that a spring tries to spring back to its original length. So if it's stretched this way, it will try to come back to its original length. So the force which does that is always pointing inwards or uh, towards the pivot point of the spring. So this force is going to be F spring is K times delta, let me call that delta, yeah, let me call it delta X, and then try to relate delta X with S. Okay, so Is that the only force acting on the collar? Am I missing a force? Weight will not figure out because this is in the horizontal plane. The weight will show up the in this direction, which you do not have it in the two-dimensional uh, uh, picture of the collar. So weight will not figure out. Okay, how is the collar? The collar is placed inside the slot, right? So the slot will exert a normal force on the collar. So I should not miss the normal force. So at this point, it's not clear if the normal force is upwards or downward. It's okay to draw it downwards or upward, whatever you like. In fact, when you do the math, the sign will show up. It'll tell you the direction. So that's the free body diagram. The only thing which I want to do here is I want to be able to resolve the forces. So I'm going to assume this is theta. So this is theta. Okay. So I think I'm all set to write the equations of motion. Okay, let's call this x and this y. The summation of forces in the x direction is k delta x sine theta. Right, sine theta is going to act this way, but that force is acting in the negative direction because it's negative to x equals mass times acceleration in the x direction. Okay, so I need to find delta x. So delta x is a stretch in the spring. Okay, the stretch in the spring is the original length minus, the current length minus the original length. The current length is the length of the spring when it's at position S, or this. So what's that? Can you find that from the geometry? Yeah, it's going to be square root of s square plus 1 square, right? Just using Pythagoras theorem. You know one side is 1 feet, other one is s, and the angle is 90 degrees. So the current length is s square plus 1 square, and the original length is the length when it's unstretched. It's the unstretched. You told that it's unstretched when the length is 1 feet, right? So it's 1. Let's try to write sine theta. Sine theta is the opposite side, which is this, divided by the hypotenuse. So that's going to be s square plus 1 square. So now I can plug these two things in the equation. K delta S is s square plus 1 minus 1 times sine theta, which is s divided by s square plus 1 square, equals mass times x is actually s double dot because s is in the direction of x. Okay, so I'm going to simplify this a little bit. S double dot is minus k divided by m, and then I'm going to take this term and then basically get rid of the bracket. So it's s minus okay, so I'm asked to find velocity when the displacement is 1 feet. So we know that s double dot is acceleration, which is v dv ds. Right, so I'm going to use that. So v dv ds equals minus k divided by m So V dV is minus k divided by m s minus s ds. Okay, let's do that integration. Okay, so initially velocity is 0, displacement is 0, the final velocity is unknown, the final displacement is 1. Right? Final displacement is s equals 1 meters, right? So that's v squared divided by 2. Top limit is v and bottom limit is 0. Okay. S squared divided by 2 is the first integral. Anybody remembers how to integrate s divided by s squared plus 1, square root of s squared plus 1? So you have to use s squared equals t and then s ds is dt and do it that way. So I'm out of time. Let me just... so if you do that, it comes out to be 2 square root 1 plus s square 1 0. Oh, I think I made a mistake. The initial velocity is 15, so my bad. So this should be 15. Okay, I'm almost done. So you can actually evaluate that because everything is known. The velocity comes out to be 14.6 feet per second. Okay. So I'll see you on Wednesday. Wait for my mail. I'll send you a mail about your scores. Hopefully tonight, but worst case tomorrow midday.